Over 86,000 Canadians live with a spinal cord injury, the majority of which occur due to trauma to the cord, such as in a car accident or a fall. The tissue damage from these impacts is complex, and every injury is different, and so it can be hard for doctors to predict which patients will regain function and which will have a permanent disability. Before we go any further, we should talk about the spinal cord. Your spinal cord is about the width of your pinky finger, and if you were to cut a cross-section of a human spinal cord, which is something I've actually done, it looks like this image on the left. In the middle is grey matter, which is shaped a bit like a butterfly, and surrounding it is white matter. The white matter is composed of nerve fibers, which carry electrical signals from the brain to the body and back again. Surrounding each fiber is myelin, a very important insulating sheath which protects the nerve fibers. Myelin is gradually lost after a spinal cord injury as the tissue breaks down, which can result in disability. If we could map which areas of the cord still have myelin, it would help doctors direct rehab and personalized treatments to help patients regain function. It would also be a valuable tool in clinical trials as a way to track myelin over time and test whether new treatments for spinal cord injury are working. The central image on my slide shows a standard MRI of a spinal cord injury, and you might be able to see a bright area which extends from the point of the injury, marked with an arrow, up and down the cord. This brightness is definitely tissue damage, but it could be caused by many things happening in the tissue. Both myelin and, for example, extra water in the tissue look bright on this type of MRI scan. So we need a scan which is more specific. Luckily, MRI is a very versatile technology, and researchers have developed advanced scans which can specifically measure myelin. In particular, we use a new technique with a long name called inhomogeneous magnetization transfer, or IHMT, which detects myelin using its distinctive magnetic properties. We optimized the IHMT technique and used it to scan spinal cords which were donated by people who died of a spinal cord injury. Here, in orange on the right, you see some of the data we collected. We were interested to find a distinct pattern in where myelin was lost above and below the injury. We found that this pattern only developed around 1 to 2 months after the injury and was not seen in patients who died before that point. We will continue to test IHMT and investigate where and how soon it detects myelin loss in different patients. Ultimately, we believe IHMT could be an extremely valuable tool to see inside the spinal cord and measure myelin loss for doctors, for clinical trials, and for people living with spinal cord injury. Thank you.